Anyway, I wanted to go back to the roots today of flyback converters, and we had a question here already on flybacks. Is why is the flyback more famous than any other high power converter at kilowatts and above topologies, like the phase shifted full bridge? Since if you read the papers, they're not going to talk too much about flybacks because it's not very academically interesting. But more of them get built. Certainly, a lot more of those get built than the full bridge converters. And flybacks are, I want to say, they're easy. They're a challenge the first time you do them. But compared to a full bridge, they're certainly easy. The first full bridge I ever built was with IBM. That was back in the late 1980s. I worked on their server power project. And it took them 7 years to go from concept to production, which is not usually acceptable these days. But of course, they demanded a level of reliability that most people never see. So full bridges are difficult. My first ever converter in industry was actually a full bridge. And I think that took us 2 to 3 years. And there was a lot of pain along the way in that converter development. And anybody working in full bridge design, high power design will know exactly what I'm talking about. Of course, when you read the app notes, you won't see a difference between full bridge development and flyback development. They make it look all pretty simple. And of course, it's not that way. They're just trying to sell you, of course, a converter control chip usually. Anyway, on with flybacks. Welcome to the webinar. This will be recorded. You will receive a copy of the recording later on. And can someone confirm in the chat? Just make sure you're getting sound and video properly. That would be helpful here. I think you probably are. But it'd be nice to get that confirmation. I think we'd get some complaints if it wasn't. Okay, let's move. All right, what are we going to talk about today with the flyback? Well, there's nothing to say about the flyback in terms of analysis or equations or waveforms or anything that hasn't already been said. But what I'm going to do is just give you, my industry overview and observations of it that you probably won't have seen anywhere. I see a lot of people making choices in their flyback and constraining themselves right off the bat with the choices that they make and get themselves backed into a corner sometimes. So some of the topics here, and I apologize, we've only got 1 hour to do this, and I can't possibly do all this in full detail in 1 hour. When we do our workshops, we spend 2 full days working on a flyback converter, both in instruction and in the lab. So 1 hour is very much a condensed version of that. First thing we'll talk about is DCM and CCM. For many app notes, and you'll see discussions actually recently on LinkedIn. People look at this as a binary choice. It's like, well, I've got to go DCM for this reason. Usually that's the choice that gets made with a flyback. Other people will say, well, I've got to go CCM for whichever topology. That could be the flyback as well. But this is not a binary choice. This is a continuum of choice. And you don't just choose one or the other. You choose the converter where it wants to be. If you read recent publications and look at the latest control chips, you would think that everything in the world is quasi-resonant with a flyback, but it's not so, as we're going to see. Right-half plane zeros, people have a phobia of right-half plane zeros, so they're very paranoid about the flyback and getting involved in right-half plane zeros. There's the RCD clamp. There's isolated feedback with the TL431. I have a love-hate relationship with that part. When I first started doing some software for it, I had to write the equations from scratch because I couldn't find them anywhere. But everybody uses it. Aerospace can't use it, but almost everybody else does. It's a horrible part. in terms of its functionality and complications, but it's just a fact of our industry. Cross-regulation is an important topic because when you're building a flyback, you almost always need more than one output. That's the whole point of the flyback, to be there. Sometimes it's a gate drive. Flyback is giving you 6 outputs for the six pulses of a high power bridge. But normally you need much more than one output. So we'll talk about that too. And snubbers and active clamps. So these are all the topic on my list. Every one of these topics could take up easily half an hour. So we'll see how we do with the timing on this. And we don't have any questions yet. Every now and then I will stop and look at the questions. So feel free to ask if you need to. And let's move on. All right, let's look at a little flyback converter design. So here's a schematic of the basic flyback, which is a single switch flyback. Transformer here with the dots in opposition, of course. I'm not going to go over the operation of this converter in detail because you can read that in any number of textbooks, app notes, or whatever. The specifications here, the low line input was 200 volts, nominal 300, high line input voltage 400 volts. This is typically what you might get if you're running off the 240 volts AC line. People sometimes have much wider specs than this because they'll be working from 85 volts AC up to 300 volts AC. And then when you turn that into DC, the range gets even wider. And that creates quite a challenge for the flyback. The output current of this, 12 volts, 2 amps. You do see that spec coming up a lot these days. I don't know why, but I've seen the 24 watt flyback coming into play. And the frequency is 100 kilohertz. Why 100 kilohertz? Why not 100 kilohertz? It's been 100 kilohertz as long as I can remember. So there's a strange anomaly in our industry that with all the inventions of the wide bandgap device, the GaN, the silicon carbide, the soft switching, the matrix transformers, everything that's in here, 100 kilohertz is usually still the answer for the switching frequency. We're very slow at moving. As you move on in your career, you'll find, well, if you move that flyback design frequency to 200, good things happen. But it's a little more troublesome in running your flyback there. And for the application here, it's an 11:1 turns ratio that we're using. And one of the surprises that came out of this webinar, and I've also been becoming more aware of these days, is you can choose almost anything you want for the turns ratio of a flyback. It's not like a forward converter where you've got to have enough voltage to get the output up. The flyback converter is really, really versatile. And it's one of the problems of a flyback is there's 1,000 different ways to design it. None of them are wrong, but there's no one single solution. So when you see people writing their app notes or their textbooks, they like to try and find the single solution, but trust me, it doesn't exist. There's 1,000 different ways to do it. And that's why it is very confusing for new people to the industry to try and, figure out, what direction should I be going in? So here's a default design of where we start. So I'm going to do this in the software in just a little bit to show you how we design a flyback. So default design for me, if it's more than 10 watts, I'll let it go into continuous conduction mode if it wants to. But I'm not beholden to that. I always retain the ability to cross the boundary between the two, to change my mind later on, to have a different version of the transformers wound. But this is a basic starting point for me. So how do we get here? Right. Well, quite a few of you on the call here have our software. This is our Ridley Works design software. And right now, this is set up for a 2-switch forward converter. Hope you can see my pointer on the screen here. So we're going to go to the flyback topology right here, and we'll click on the flyback. All right. As soon as I've clicked on that, believe it or not, the design is done. Okay. There's no thinking, there's no testing, there's just the flyback design is there. It's not a CAN design. We change the specs, we will change the design. And we're going to see how we can push that around a little bit. I have an unfair advantage here in that, I write the software and I use the software. So when I design a flyback, it's an easy task for me. It's about 10 minutes to go start winding transformers. So let's make sure we get our frequency right here. You see right now it's 196 kilohertz. We're going to change that to 100. Click OK. And the converter is redesigned at 100. What do the waveforms look like? Here we go. Here's the waveforms that you're seeing in your presentation slides. So we've got 2.8 millihenries on the primary. We've got this amount of ripple here. And the thing that tells us it's continuous mode is that there's a jump when the switch is turned on here. And then the ramp comes in here. If I move my inductor down a little bit, it would increase the ripple current. And if I move it up a little bit, it will decrease the ripple current. Okay, so we can reset that back to the default value. We can continue the simulation. But by the way, inside the software here, we have the simulator. This is not just a waveform drawer. This is true simulation. We're just showing a little clip of it here. So if I turn the time scale down to the minimum, we can't even see this because there's so many cycles in. There's 800 cycles of simulation here. Let's go through startup. So here's the startup of the converter. You see current limiting and then current into regulation. And of course, we've got to zoom in a little bit to be able to see that. So I'll turn the time dial there a little bit. And now we can start seeing the switching waveforms. So we do all this inside. We're not using LT Spice. We're not using anything like that. And the whole point is that during the design phase, I don't want to be looking at equations. I don't want to be working in MATLAB, MathCAD, pushing numbers around. I want to see waveforms, and I want to see them now. I don't. If I change my, let's zoom in as we were before here. Okay, there's my startup coming in. I'm looking at what's happening during startup. Let's hit continue. Here's my waveforms. It's like, hey, what's going to happen at highline? So you click this button here, it goes to highline. And there's my waveforms at highline. Okay, coming into steady state. And you see at 400 volts, and it's still continuous mode in this particular case. So you get this visual feedback immediately of where you are in the design. Okay, so let's go back to minimum line here. And you say, well, do you want to leave the design at that point? And you may say, okay, well, I don't like it as continuous mode. You may have a boss who's been burned with continuous mode before, and they say, no, we're not going to do that. Let's make it discontinuous mode. I don't want to be continuous mode like that. Lots of reasons for that. We'll see them. So you just check this little box here, and we're in discontinuous mode. Now we hit continue. Okay, so now we see the current is starting from 0 here at the low line. You have to check low line. That's where it's most likely to come out of discontinuous mode and head into continuous. If you go to the max line, of course, it's deeper discontinuous. You can see much narrower pulses coming along in the converter. Okay, so what's the right answer here? Should we be discontinuous mode or should we be continuous mode? Let's do that again. Hold on. Change my scales. Continue. And fix the vertical scale here. You see in discontinuous mode, you're asking for a narrow current pulse here of 0.7 amps. And if you went to, discontinuous mode. There's my discontinuous inductor right there, 0.7 amps. My continuous mode inductance. Oops, don't want DCM only, I want continuous mode. Reset. Continue. Okay, it's only 0.45 amps in there at high line, and it's 0.5 a high line. So we've got a low line. So now we've got a trade-off. How much peak current do you want? How skinny do you want that pulse to be? There's no right answer to this, okay? Design it where you like. When I'm doing a converter design, I will literally wind 10 transformers and see where that converter wants to be. Okay, so that's how we do this in here. Let me bring up the slides again. So there is our continuous mode, and we had 2.8 millihenries in here. Here is high line, still continuous mode. And then we have the option, if you decide you don't like this ripple current here, you say, well, I'm not going to go with that. I want to go more into continuous conduction mode. So I've got much less slope here, from 2.8 millihenries to 5 millihenries. So now I've doubled my value of the inductor. I don't know if that's a good thing yet. If you design by old school rule books, looking back into textbooks from a long time ago, if they're doing a boost converter, for example, they'll say, well, we want low ripple, we want 10% ripple or 20% ripple. And sometimes people carry that rule forward, not usually into the flyback, but some people do. But the point is, nobody really knows where this ripple should be, and you're free to move it. And that's okay. There's much more to this, of course, than just looking at this waveform. It's going to affect the control, it's going to affect soft switching, it's going to affect many things. So here's our low line continuous mode, 0.4 amps here. Here is our low line discontinuous mode. And again, we're changing these values at will here almost. Okay, again, there's no canned solution to any of this. And that's the struggle that the poor semiconductor app notes people have to deal with, is that they can't find that canned solution and tell people where to be, because it does not exist. Anyway, do you want to go further into discontinuous? Well, you can if you want to. You can go deeper discontinuous mode. So it's 200 volts, 200 volts, and we've gone down to 0.69 millihenries here, so that's 690 microhenries. And if you're involved in winding transforms, you say, wow, if I've only got 690 microhenries to build, it's going to be a lot better than that 3.6 millihenries or the 5 millihenries. But at some point, getting smaller on the inductor doesn't work out, and you find the switching losses suddenly start climbing on you. So, don't follow that trail of just making that inductor smaller and smaller and smaller, because there's less and less turns on the inductor core. It's going to penalize you in some other way here. All right, let's talk about quasi-resonant. So quasi-resonant is when you turn off the flyback, this voltage here goes up to the input voltage plus the reflected output voltage. I'm getting some feedback here from something, but I don't know what that is. So here we've got the input voltage plus the reflected voltage coming along. And then when it goes discontinuous mode, the inductance of the transformer is going to ring with the capacitance of the diode and the transformer and the FET. And it's a very, very complicated mechanism going on here. This waveform is very much idealized. These ringing waveforms do not look like this at all. Okay, they're distorted sine waves. They get broad at the bottom and they get very peaky at the top. So trying to decide actually what the ringing frequency even is there is difficult. So the quasi-resonant has been around for a long time, and the plan is that when this voltage here rings down, you switch at the bottom of the ringing. And then when you turn on, you're discharging a semiconductor capacitance. It's not much, but it's significant. And the amount of dissipation you have from turning the switch on there, will be reduced if you turn on at that dip. So this is what they call quasi-resonant. And it originated actually way back in the 1950s. And in the 1950s, they were using Flyback supplies for the cathode ray tube in a TV set. And it was running at 14 kilohertz in the US. It was running, I think, 22 kilohertz in Europe. And they couldn't tolerate the hard switching because it would generate a pulse of EMI, and the pulse of EMI would get involved in the sweep across the screen. So you could actually see it during the sweep on the screen. Now, of course, you're receiving an analog radio signal or the TV signal, and if you're switching your converter and you got that peak of noise in there, it's going to interfere with the received signal. So back then they built what I would call a true quasi-resonant, where you force this voltage to ring all the way down to 0 before you turn it on. So that would be the 0 voltage switching. So in order to do that, you have to change the turns ratio of the transformer, because the reflected voltage here has to be equal to the input voltage. So you've got to take the output voltage, the 12 volts in our case, plus a diode drop, scale it up by the turns ratio, in this case multiply by 30, and that gets us up to about 400 volts to give us 0 voltage switching. So that's an interesting challenge to do that. So let's go back in our software and see whether it can handle that. So right now, if we look at our turns ratio in the transformer, it tells us, okay, I want an 11-to-1 transformer. It's actually 10.6 at this point because we haven't done the detailed design yet. So then you're going to say to it, well, I want 30-to-1. I'm going to shift it by a factor of 3. It's like, well, that's kind of a bit crazy. I don't know if that converter is going to work. I don't know if there's enough voltage out there to deal with 30-to-1. So give it a try, right? And now we look at we want DCM only right here. Okay, see where this is. Oops. And continue. And then we'll take a look at our output voltage. Here's our output voltage, and it's like, oh, it's not there. So because I stepped so much down in with the Flyback with that transformer, 30-to-1 transformer, now I've got to get it deeper into discontinuous mode to bring the gain back up. So I have to reduce the size of the inductor. Okay, each time I reduce that, let's see, the output voltage starts climbing. So continue. Okay, now it's at 11.6. Continue. Continue one more time, and now we're back at regulation here with 1.2 millihenries. So when I step down that much, now I've got to ask the converter to give me a much narrower pulse, a much deeper into discontinuous mode. So now this is my pulse on the primary side, hitting almost 0.8 amps here from a 400 volt source. And if I go to high line, well, now it's an even skinnier pulse here. Okay, so if you want that true quasi-resonant, you got to do that big step down to get the 0 voltage switching. So now we've got DCM, different degrees of that, different degrees of, CCM and different degrees of that, DCM, different degrees of the DCM. Now we've got to decide, okay, what's the turns ratio of the transformer going to be so that I can get this 0 voltage switching, or do I even want the 0 voltage switching? Now, back in the day with the early TV sets, they didn't have to go from 200 to 400 volts. They had a much narrower range of AC line coming in. So the rest of the electronics certainly wouldn't have worked if you tried to give them a full 2-to-1 line range. So their job's a little bit easier. This is much easier to do if you have a narrow range on the flyback. Okay. So anyway, there you go. So we've got that design done. Let's pull up the presentation again a little bit. So there's our 30-to-1 step down. That's about what we ended up with on our inductor value. And now, sorry, let me go back into the software. We say, okay, well, I'm doing this narrow pulse here. And then if I go to the maximum input line, it's even narrow. Now let me look at what's happening in the secondary side. And on the secondary side, all right, we're off scale there. Let's auto scale that. You can see we've got this secondary pulse now, which is extremely narrow, getting through to the output. And that's because of that 30-to-1 range that we put on the transformer. And we're not yet in quasi-resonant mode. See, we're going constant frequency here, and then we're wasting this duty cycle right there, and we're not taking advantage of the soft switching in this. Okay, so we've done all the things we need for quasi-resonance. Now we need to put the right controller on it. Let's check the quasi-resonant box here. And there you go. Now we're in our quasi-resonant mode. Look how the currents came down there, which is quite nice. Okay, let me zoom in a bit. Why am I having to zoom in? Because in this particular case, the quasi-resonant converter is now running at 500 kilohertz at high line, because I took in all that dead time. I said, okay, I'm going to switch without that dead time. So now what am I designing? Is this a 100 kilohertz converter, which where we started? Is it a 500 kilohertz converter? If I go low line, is the minimum line here. Continue. And now it's 250 kilohertz converter. It's like, I don't really like that. Let me up that inductance a little bit more. Let me make sure it's still running. Low line. Let me bring the inductance up a little bit. Continue. Okay, look at the output voltage, make sure it's still good. Okay, we're still running at 12 volts, but I was able to bring up my inductor value again, because now I've gone into quasi-resonant mode. I'm getting more gain out of the flyback. But there's an interesting thing that you see here, is that this is now to 190 kilohertz. If I go a little bit higher in an inductor, I bring down the frequency each time. So there's 160, and then I think this is what is in your course notes, is down to 140 kilohertz. So I'm getting quasi-resonance. I'm approximately where I wanted to be, which is, I have to crank the inductor up a little bit more if I want to get it down to a lower frequency. But this design, you see how it's shifted all over the place here. And none of these are wrong designs, but I don't think you want to take that frequency up to 500 kilohertz unless you're really ready for that kind of switching frequency, which most people aren't, because most controllers aren't ready for it. Okay, so you can see the complication here and the fact that there really isn't a fixed solution to this problem. Now, something else that's very interesting has happened is that when people design their flyback converter, they say, well, I'm always going to design it less than 0.5 duty cycle, because they've heard that bad things happen at 0.5. They want some time to just reset things and protect things. And there's the current mode control issue with more than 50% duty cycle. That goes away with a higher duty cycle. But because I've killed all that dead time, the 50% duty cycle limit has gone out the window, and it's just naturally switching itself now at 64% duty cycle. So we've kind of thrown out the rule of our max duty cycle of 50%. Now we've got a 65% duty cycle, and then it's like, well, what if I redesigned that original converter with a 65% duty cycle instead of a 50%? And then you're going around the whole loop again. It's like, wow, maybe that continuous mode converter would be happier at a 64% duty cycle. So you can see how you can stay in there for some time. It's a lot of fun inside this program, inside Ridley Works. If you're doing this with LT Spice, this is all a nightmare. You're going to do one iteration, you're going to change a component, and then you say, okay, good enough, I'm going to stop. but we change things very quickly. And another thing that we do that gives an advantage over the LT Spice approach to it is that when you've changed the inductor size, you move to a different point, and what you get, you've got to simulate it to steady state. And for us, that means you've got to put the control loop in place. So our control loop is always in place and always optimizing itself for every one of these inductor values. Greatly accelerates your design process there. So where are we now then? Let's have a look. So there's our quasi-resonant. We can get to our quasi-resonant there. We can, the frequency changes as I just showed you. It goes to 140 kilohertz. The duty cycle is now much more than 50%. And here's the duty cycle at Highline, which is now 0.454 and about 300 kilohertz. So this is ranging from 140 kilohertz to 290 kilohertz. I'm no longer choosing the frequency on step one, because as I designed it and went quasi-resonant, it went and moved its frequency. So now you say, okay, well, if I want to redesign, I've just got to resize everything again. So I hope you see and feel the iterative process here that, you get this out of our software. And I also expect you to get that out of your hardware. Don't be restricted in just winding one transformer or getting it from your vendor and then being satisfied with that. Okay, you've got to be ready to iterate here. Management never likes that, of course, but do it on the quiet. Build the transformers quietly. Don't tell them you're trying many different things. Okay. So if we were to redesign, I'm not going to do this in the software, I'm just going to show the results here. You could redesign the continuous mode with a 0.64 duty cycle, okay, which was the same as the discontinuous mode, and then go to 200 kilohertz to make it a fair comparison with the discontinuous mode. So that's between the 140 and the 280 end up. Now you've got this better comparison. You won't see this in any textbook. Nobody's going to do this. They're going to design a fixed frequency CCM, you're going to have a fixed frequency DCM, then they'll go quasi-resonant, and they'll have moved all the parameters around at the same time. Okay. But when you go CCM, going above 50% duty cycle, I really dislike that people constrain themselves there. We don't do that in our designs. We let that duty cycle go out to typically 80% worst case, because you get so much more gain out of it. So if you're running 80% duty cycle, D prime is 20% duty cycle, you've got a gain of 4 just by allowing yourself to go to the bigger duty cycle. Then you can step down more with the transformer. You've got less stress in the secondary. Everything gets better if you can let that duty cycle grow a little bit. So that's another thing to think about when you're doing your designs. Like you needed more to think about, right? Okay, let's talk about the transformer. I'm not going to dwell too much on this. I'm just going to do it quickly, but this isn't quite the point of the presentation. But those of you who've used our software, have come to the workshops in the past, we've always had it be a very manual process, because I want you to choose a core, choose the winding, try different configurations, see what happens. So we have automated that. And the term we have for our automated designer is Ridley IQ. There's nothing artificial about it. It's high intelligence that's gone in here. It's 40 years experience from me, another 40 from John, another 40 from Art, and just looking at the industry over the years, we can design, things in a much better way, I think. So we've got this high-level designer now in RidleyWorks. It takes all the hooks that were in there before and says, okay, let's automate this process for you. You're not usually in our workshop when you're using our software. You're trying to get your designs on. So you're not in learning mode. It's like, don't teach me, just get me to the answer, is what we see from industry these days. So it'll do core selection, winding design, core losses. It'll do proximity losses for you. It'll do multiple designs in a very short space of time. So let's go see that working. So where do we end up here? We're in quasi-resonant. Let's take it back to our nice continuous mode converter. Okay, and reset this. Continue. And I don't want that 30:1 transformer anymore. Let's take that back to the default value when I'm in continuous mode, and my frequency is going to be, did I say 200 kilohertz on this? 200. Okay. And then I look at my currents. There we are, back in our continuous mode again. All right, this design. Let's make sure the output is regulating. There we go, running right around 12 volts here. Again, apologize for the speed here because we've got limited time in doing this. Let's go design a transformer for this thing. So we click on Transformer Design.
Transformer Designer.
Okay, and you will see here that you have a schematic of the transformer. This lets you go piece by piece for those that like to do it themselves. And then what we've added now is this Ridley IQ in here. I'm going to take it back to just the 100 kilohertz case, just to be back where we first started the design. Let's click, make sure I'm there. Continue. There we go. There's our 2.85 millihenries starting case. I don't want to move too many things while I'm doing this.
Designer.
Okay, we say, okay, here's your options. You can do it manually, or you can use the Ridley IQ. If you want to use the Ridley IQ, you can choose a specific core in here. Sometimes it's like, okay, we used this core last time, let's use that core again. So we'll go ahead and use that core again. So we're going to use the RM family. Then we're going to choose magnet wire on the primary, and then we're going to do a triple insulated secondary here.
Wire secondary.
Okay, and then you just click on the button.
Simulating to steady state.
So the first thing it does is a simulation. I don't know if you can hear it talking to you here.
Core selected.
On the microphone.
Optimizing transformer primary winding layers.
Okay, so the first thing it does is it optimizes the primary. You can see it actually counting through different layers of primary winding here. It goes up to 4 layers. Then it goes back down to 3 as being the optimum. So it's done a 3-layer primary, and then it split it. It sees multiple layers. So, hey, I don't like that. I don't like those multiple stack ups without doing a split.
Optimization complete.
And then it designs the secondary as well.
Total transformer loss 0.238 watts.
Okay, it's very low loss. The reason for that is there's actually a pretty big core. It was shooting for 0.34, and then it was the closest one to that that's bigger was the RM8, so it went for the 0.54. You can steer the design as much as you like. So you can choose a specific core. These are the ones we have so far in here. We're always working on these. So you could have done the RM6 core if you wanted to. Or if you want, let's see, let's choose an EP17 core. No, that one's not quite big enough there. Well, it's about 0.3. Well, we'll go RM6, why not? And you say, okay. So we've got a specific core. And you just say, well, let's design it again.
Simulating to steady state. Core selected. Optimizing transformer primary winding layers.
And then we go through, another design. Now it's going to end up with 4 layers on the primary because it's got actually 5 layers on the primary.
Primary optimization complete.
And going through
Split
the secondary again.
Design.
Needs more turns on the secondary because it's a smaller core.
Optimizing secondary winding layers.
And the losses have gone up,
Optimization complete.
But they're still reasonable. So there you go. You have an RM6 design, an RM8 design. At any time, you can save a design. And then you've got the result. So here we're compounding all our choices for Flyback. We started out with, well, we didn't really know where to be in DCM. We didn't know where to be in CCM. Now we don't know which core we should choose if you want to choose a specific core. You can let it choose for you. Well, should it be this family, this family, this family, this family? It doesn't matter. But this is why nobody ends up with the same design. Nobody. And the freedom to go choose different cores and different layouts is, it's the recreational aspect of power electronics. So I encourage you to explore that, and don't stress so much on getting that right solution first time on your board. Okay? Just figure it's going to be wrong, and we're going to do it again. And we're going to do it again. okay? But get very, very fast at doing it again. That's what I would encourage you to do. Okay, so let's go back to our slides here. So we did the design 2 times. One was for continuous conduction mode. This one, here's a different example where we did that RM6 design. And then this one, it gives you the total losses here. This is continuous mode. This is discontinuous mode, continuous, discontinuous. And this is the leakage inductance of the transformer. And then we did the design again. So the turns ratio went from 11 to 1 to 30 to 1. We designed it quasi-resonant at a different frequency. And then the design was repeated. So now you've got a second design here. Here's an RM6 design. Number of turns is kind of interesting. Didn't change that much. The inductor value didn't change that much. And then the secondary winding, so 22 gauge is 20 gauge here. We needed less turns on, no, we needed less turns on the big step down one than we did on that one. So now you've got these two totally different designs on the transformer. Wind them both, see which one you're happy with, and then you make a choice. Do I want to go with that quasi-resonant? Do I want to deal with a more complex controller that's going to make that happen? Do I want to have that big step down, and more stress on my switches? So these are all valid choices, things that you have to decide that you're, where you're going to be on the design continuum here. All right, what about the next thing? This discussion's been going on this last week, actually, with some people chiming in. It's like, no, you don't want to go continuous mode because you got right half plane zeros. And like in the discontinuous mode, they're just going to go away. Well, they sort of do, but to be honest, this is not driving your design. Here's a 5 millihenry CCM converter, okay? And we're crossing over here. We got tons of phase margin. This was the low ripple case, so we went overboard on the size of the inductor. Now you go for the 2.4 millihenry. Say, well, that lets us cross over a little bit higher, but this is fine. This loop is fine. The performance here is fine. There's plenty of phase margin. There's plenty of noise rejection. You've got the output impedance down. And then if you go DCM, the crossover gets out to 10 kilohertz. Well, it also almost got there with CCM as well. So there isn't really, this right half plane zero is not a driver for the power stage. You choose the power stage where the power stage wants to operate. Okay, you don't want super narrow pulses in your converter. All right, they're not going to look like that on the real hardware. I was planning on doing some hardware demonstrations here, but there's no way. We've got too much going on as it is. So anyway, don't worry about the right half plane zero. We will show you where it is. We will help you predict it. But it's just going to move your crossover frequency in the converter. So let me not show you that. I could show you that in the software. We can do that after we're done here during the question part if you want to, where we do the small signal as well. But let's talk about that later. So you've got the curves here. All right, don't be afraid of the right half plane zero. Embrace the right half plane zero. Put it where you want it, and then control the converter as you like. Nobody really wants a super high bandwidth loop on a flyback converter. All right, you want them in a buck converter because it's for a point of load and it's got drastic step loads on it, and you don't want a lot of capacitance there. With the flyback converter, if I see a crossover frequency above 1 kilohertz for the production supplies that we test for people, I'm happy with that. So no one's getting super aggressive on these loops. So this is not a driver for the design in my book anyway. But there again, I've been dealing with right half plane zeros a long time. So what's more important is that you get rid of the double pole, because when the right half plane zero restriction runs into the double pole, that's when you get into trouble. So in the good old days of design back in the 60s or the 70s or 80s even, the LC filter frequency, well, it might get pretty close to that right half plane zero frequency. And then suddenly you're designing a loop where you're in this region here where the phase is changing rapidly. So you can't do a good job. So the more important effect of DCM is to get rid of the double pole, not so much the right half plane zero. That just is what it is, and we don't worry about that. But make sure, of course, when you're designing low line, full load is the key. The resonant frequency goes to its highest. The right half plane zero frequency is at its lowest. So as long as you're okay there, everything's fine. But don't go DCM to get rid of the LC filter. Put current mode on the system. Current mode gets rid of the LC filter as well. So not too many people do voltage mode flyback converters. Maybe students coming in, they're a little afraid of current mode, so they won't use it. They'll use voltage mode. And just use current mode. Don't worry about the which mode you're in when you do current mode. All right, burning through here. Let's see, I've got 8 minutes. RCD clamp. I have a funny history with the RCD clamp. I was doing, we took our Ridley Works software and we were implementing that for onsemi for a little while. And they were using the NCP 1200 with an RCD clamp. And I started digging around. We had to design the entire converter for them, of course, including the RCD clamp. And I couldn't find anybody had done the math for the RCD clamp. Doesn't mean it's not out there. It just means I couldn't find it. And I looked hard, and the onsemi people looked hard as well. So with the RCD clamp, you have the flyback voltage here, which is the input plus the reflected output voltage, and then you've got the clamp voltage on top of that. So you're using this little RCD network. This is a big cap and then a bleed resistor on it. So this is just clamping above that maximum peak there. If you want the analysis of this, click on this in your PDF file and you will find the article. And if anyone can find an article that came out earlier than that on the RCD, let me know. I haven't seen one. So in my mind, I did it first, but that seems highly unlikely, so I don't know. What is there to know about the RCD clamp? The dissipation is higher than the energy storage in the leakage inductance. Okay, that was the surprise when I went through the analysis. And the harder you clamp it, the more dissipation that you have, because the voltage source keeps feeding energy into it. If you try and clamp that harder and harder. So don't do that. Let that clamp voltage go up and be higher. Okay. Does everybody use the RCD clamp? Well, you'd think so if you read the app notes out there. All the products I've done, we didn't use the RCD. We used an RC. I always start there with an RC. If I can get the voltage ringing under control with the RC, I'm not going to add the clamp because it's always going to dissipate more and it's always going to add, more complications to your circuit. So don't assume that you need the RCD clamp. Okay, and that applies really to just a special class of converters that the app notes talk about. Okay, RC snubbers. You put them on the diode, on the primary and the secondary. We've got the same article here to go read. Go click on that. You could read the article. It's also a download for you. And funnily enough, the same thing happens with RC snubbers, that the dissipation is going to be higher than the energy storage in the leakage in almost all cases. So it's not just 1/2 Li squared times the frequency. Okay, it's actually more about the value of the cap. You've got to charge up the cap and discharge the cap. So it's actually 1/2 CV squared. The more you damp the circuit with a bigger cap and a smaller resistor, the more dissipation there's going to be. So we always end up in an intermediate range here where I'm damping enough to maybe a Q of 1, but there's still some ringing going on. But if I damp more, I'm going to lose efficiency. Okay. Beware when you look at equations in this text. They are approximate. Why are they approximate? Because we have an inductance that moves with frequency quite a bit? And are you taking the inductor value at the frequency at which the clamp is ringing, or are you taking the leakage inductor value that the manufacturer is giving you, or that you measure at lower frequencies? Got to deal with that. So there's a weird equation for the inductor for its value. Then the capacitance of the FET is nonlinear. So it goes by one over the square root or something of the voltage across it. So when you look at the ringing waveforms, there's a sharp peak on them where they ring a high frequency and that low frequency at the bottom. So it's got a nonlinear cap. Then it's got the linear value of the transformer coming in. And then it's, normally the diode is not involved in that snubber because the diode is turned on now. But nobody's written the exact solution for the equation for that RC snubber because it just doesn't exist, to be honest. All right, never mind. It's empirical. Active clamp flyback. Well, here I've got two switches. Here's my flyback switch, and then here's the active clamp switch, which needs a high side drive, then it goes into an R and a C, and you got to get the timing on this right, and you got to control this just right. Sometimes, I don't know, is the resistor always there? Why don't I know? I don't like them, to be honest. There's lots of chips available for them. I'm sure when you debug them, they're fine. But I'm not a fan because my job, in doing designs for companies out there, we do a lot of industrial design. My job is to make sure none of them ever fail. And this is a lot of complexity that has problems. If you put short circuit on your flyback, if there's a transient, a startup, they can all, go south with the active clamp. So I see people struggling to get through this through their development phase. Again, once you've got it, once you know all the quirks, no problem. Anytime I see this high side drive on this FET here, it's like, give me a 2-switch flyback. Then it just clamps everything, clamps it hard to the rail. All the leakage energy goes back to the rail. There's no control going on. And this little 2-switch flyback thing didn't used to be a thing until maybe 10 years ago. I started seeing more and more of this. The Canadians used it because they had a 600 volts AC rail, so they had to split the voltage for the FETs. But when you first see this, you see the two switches in series, you say, well, that's got more on resistance, got less efficiency, but that's actually completely backwards. When you put two in series, you've got lower on resistance because the voltage, the on resistance of each individual one at the lower voltage rating is better. All right. Worst case analysis of the 2-switch flyback is a lot easier than that active clamp. So there you go. TL431. Desperately running out of time here. I mentioned earlier, love them, hate them. The analysis of it is a bear, okay? Because it's not your normal type 3, type 2 compensator. It's got a path here. We actually build a type 1 around the air amp, and then the type 2 comes in through this. But you're heavily dependent on the parasitics of the circuit, the resistance of the diode, the optocoupler path, and how that's going to degrade over time. So, it's in our software. We've written it up. You'll find it on our design center. So I encourage you to go there for that. Let me talk about a little fun project here, and we'll wrap it up with this. This is my first ever design project. I was called on in this in about 1991. This was for a 10,000 amp circuit breaker for GE. And I got called in because a friend of mine I went to college with said they needed a flyback circuit. And at GE, with all their industry experience, nobody knew how to design a flyback and they didn't want to learn. So they called me in as a fresh grad from Virginia Tech to do this for them. I didn't have any industrial experience at that point. I didn't know how to do the layout software. I had to hire somebody else to do that. But muddled through the project. It was a 12 volt to 240 volts AC, 12 volts DC to 240 AC. There were 4 versions. I see so many people struggling. It's like, well, I got to have it wide range across this whole range, no changes. It's like, push back a little bit, okay? If you can rewind the transformer with 4 different versions, it's going to work way better. Don't kill yourself here because somebody from purchasing said, no, we only want 1 version. That's not fair. It has a 24-volt output, 0.5 amps, an auxiliary at 0.1 amps, and a bias winding at 50 milliamps. Safety isolation. We used a 2843 controller, more than 50% duty cycle. That's to get the gain to cover the range that we were going to see. 100 kilohertz switching, RC snubbers only. There was no feedback across the isolation boundary. There was no room for any feedback parts. And it went on an RM6 core, which is what you see right here. And the biggest problem we had on this was the regulation. So we needed a 24-volt output with a 20-to-1 load range here, and a bias winding that was for the control chip. And we wanted to regulate off this because I'm already on the primary side at that point. I'm not going to cross the boundary. So the first attempt at winding the transformer was like, okay, wind a primary, and then when the secondary is kind of bifilar with each other. And this was a disaster. This gave 20% regulation for the converter. 3 weeks later, nothing but winding transformers again and again and again. We got the regulation plus or minus 2% on this. So that was pretty cool. It's all about the transformer, okay? It's not about the control scheme. It's not about, you got to add a TL431. You can get really good regulation if you get your transformer right. Okay, not enough time to go over that here, unfortunately. You get that when you come to our workshop for sure. But we spend a long time on that. So here's the project. Here it is in the book. This was enabling a 10,000 amp circuit breaker. And the intricacies of this transformer wind enabled this entire 10,000 amp, project. So this was all good, and I built this, put it into production, and then didn't hear anything for a while about this project. So it's like, okay, well, they probably found another way to do it. Until 31 years after the design, I got a phone call. This was last year from GE. And they said, you remember that Flyback power supply design? It's like, well, sort of. He said, well, we're having a problem with it. It's like, okay. So my first question is, well, how many of those of you, are you still making those? And they said, yes. I said, wow, that's really impressive. Who's making the transformer for you? Because that was special. They didn't know, but somehow the knowledge of the transformer had carried forward. So that was cool. And then my third question was, well, how many of these have you built? And the answer was, well, 350,000 of them. It's like, whoa, that's good. That's good. So it's not that I'm a great designer. I had some good help on here, but we just went through this design rigorously and we made it fundamental. There was none of this active clamp stuff going on. There was nothing in there to fail. And when I look back on this project today, if I were to redesign this Flyback, I don't know if I would change a thing, to be honest, because you can't argue with that much reliability for that long. So, but the problem that they had after 31 years is that the vendor of the control chip, is that 2843, had changed something on their latest revision. So some little sub-specification had dropped and suddenly the converter wasn't working anymore. So their solution was easy. They changed to the other vendor because we had 3 vendors on that. So the multi-sourcing of the control chip was hugely, hugely important to this project. Okay, so this is always one of the great mysteries to me of modern design, is why people are happy with that single source controller. Because if it goes wrong during production, you only got that single source controller. So a lot of when we do industrial design, we try to use something that's got more than one source. And a lot of our customers are aerospace, space people, and so on, and they're very much the same mindset. They want tried and true and tested and multiple sources in there. So anyway, that was kind of a fun wrap up to this converter after all those years. So good stuff. I'm sure many of you have the same kind of story as well. All right. Let me have a quick check to see if there's any questions. We have no questions here. Does anybody ask any questions? Do we have any chats? I'm sorry, Denise? I'm sorry. All right. So anyway, no questions, I guess. Well, that's always good. You can always send us some questions later on. Want to learn more about what we do? Ridley Works. I don't know how anybody designs without it, or why anybody would want to at this point, because it's so much easier going through this process. It's not expensive. Okay, costs you about $1 a day if you get the 3-year license on that, and so that's available. If you want to send an email here, if you want a full demo of the software, we can provide that to you. Power supply design workshops, these are ongoing. We don't have many spaces left for September. So if you're thinking about signing up for September, get in there soon, because there's only, a handful of spaces left for that. And then we've got October over in Europe, and then we're back here in Camarillo in December again. So think about coming to a workshop. You meet lots of people just like you, and get some hands-on. The big deal about our workshop is, yes, we have theory, but it's hands-on. You build things, you build flybacks, you wind them. Frequency response analyzer, the granddaddy of them all, is the AP300 analyzer. This has kind of become like the HP4194 of its time. In fact, this replaced the HP4194. The person who came up with the analyzer used to work for them. So all of our space companies, military companies, go for the AP because it's got full military calibration and everything that they need in that industry. And then for the commercial companies, we've got the Ridley box, which we developed during COVID, and people liked it so much we made a product out of that. So we're there with our frequency response analyzers. Come join our Facebook group, and I know it's Facebook, and everybody hates Facebook, but we have a lot of good activity in the Facebook group. In here discussing this, there's 7,000 people talking about things related to power supplies at a very good level. If you want the current mode book, you can get that from our website. These are all clickable links. And if you like this webinar, go and click on the articles here, and you'll see we have a lot more webinars in there, just like this one. Okay. And there's the Ridley box. Yep. So that's it. Thank you all for your attention. Good to see you all here. I think you're going to get a little.
Can you hear me?
Question. Yeah, I can hear you, John.
Oh, so yeah, over on the right-hand side of the webinar, under the question marks, there's a whole list of questions. I've been answering them as fast as I can go, but there's a lot of them there.
Oh, I see. I'm on a question. Oh, good Lord. Sorry. 80% allowed duty cycle. Let's go down the list here. Okay, yes, yeah. I've run up to 80% allowed duty cycle. It's 100% duty cycle trip, the 2843. And 80%, we practically limit it below that. Okay. Yeah, thanks, John. Thanks for pointing that out. No, you don't have a 50% duty cycle limit on flyback. You do on the 2-switch flyback, but any other flyback, no, you don't. How to get the presentation? You should be able to download the presentation. It should be there. I see John's. How is the core selected? Well, it's an inductor. If you go on our website, our design center, we talk about selecting the core. It's based on the peak current you're going to see, and it's based upon the inductance that you want. And then you choose any core will do, as long as it's about the right size. That's the thing that drives people crazy. Any core will do. They want to be told, I want this core. This is the right one. There is no that. Okay, thanks, John. Thank you, John. Would we consider going to North Carolina? Yes, we would. So if anybody wants our workshop in their region because you can't travel, if you have a group to make up the course, yes, we do travel. So, hopefully it's a nice place. We've been to Texas, which was nice, the bit we went to. We went to Paris with the workshop. We've been to Germany and Italy and various other places. So let us know what you want if you'd like a workshop near your place. Okay, yes, this is a lot of questions. Well, we'll stay here as long as we need to. Okay, back to the top. Can't see. How you design current sense resistor and output kappa flyback. Ridley Works. Everything's in Ridley Works. Everything. Okay, 40 years of my knowledge is in there. So again, why you wouldn't use that is crazy to me because it's just not expensive. Active clamp. How to avoid multiple resonance in active clamp flyback. Sorry, you know my answer, right, John? Don't do the active clamp flyback. All right, just don't. All right, it's a pain. Yes, you can solve it. It's a pain. Don't. Is there a guide for it? Somebody said. I don't know. A guide for Ridley works. Yes, you can get the manual from our website. 80% duty cycle. Our core is selected. Yes, we'll come and travel to you wherever you are. So contact us. Send an email to info@Ridley Engineering. Question regarding the active clamp flyback performance, conventional flyback. Is it worth the target active clamp forward flyback? No. Yes, you can make it work. For me, no. I've done up to 200 watts on a flyback, no active clamp, but I did a 2-switch flyback, so I don't plan on, complicating that. Is this in, sorry. Would you typically use a TL431? I will help you use the TL431. I'm not putting it in my designs unless I really, really have to. Okay, don't like them because they're too twitchy. They degrade over time. You don't know where they're going to start out. And a lot of our customers just don't want those. So there's lots of other ways to isolate if you have to cross. Will Ridley Works support LLC? Absolutely. It does LLC. Does it do LCC? No. Okay, nor will it. Okay, but LLC is quite prolific these days. And yes, we do that. And it's kind of like the Ridley IQ button. You put your specs in, you click Ridley IQ, it chooses the components of the LLC, and it's straight through. There's no iteration in there involved, which is great. If my output voltage is not regulated, is fluctuating in hardware, what is the issue? Start with the transformer. That's my TL431 question. Any plan on future or focusing on the, oops. Sorry, I lost that one on future webinars on analog. Here we go. The analog circuit design part, sensor design, focusing on IC selection. Yeah, we can do control design if you want to. There'll be a survey when you get off here. It will also get mailed to you about what you'd like to see for future topics. And also there's a bigger question in there. Would you like to see much longer webinars where we charge you a fee for it? Because there's a lot of preparation and it's a real learning session. Maybe we take the whole day to go through it and step you through it. Okay. How to reduce switching loss if doing hard switching? Well, switch faster. And that's a bit facetious, right? Sometimes, there's an interesting aspect of that is that the modern trend is, we got to shrink leakage. We got to get leakage down. We got to get leakage down. We got to get leakage down. And when you do that, you lose the benefit of leakage. Leakage actually gives you zero current switching to some extent because you turn on the switch. It takes a while for that current to get up. So if you work desperately hard on getting the leakage down, your switching loss is going up. So don't go overboard, okay? Don't go overboard. All right, bidirectional synchronous converters. Yes, you can. Does Ridley IQ, does toroid cores? We've got them in there. We haven't put the design algorithm yet because I realized over the last year we're working with a downhole company. Toroids are weird. They've got this huge, huge winding length where you end up with lots and lots of strands. So we're gonna we're going to get to that next. We're going to do planers as well in there. So, give it a try. Don't wait for these features to come in. The more of you that get Ridley Works, the more we'll develop it, the more of these webinars we're going to do. If everybody here bought a copy of Ridley Works, I could do nothing but webinars. So think about that. I'm sure your companies will spend the money. What we use instead of TL, good Lord, there's a lot of questions, John. Any plan on analog? I got that a little more the way you choose. How do we get 2% with the winding distribution? Okay, it's a funny thing. We do that in our 5-day workshop. And one of the things I tell people in the workshop is we're never going to publish this because this is the most amazing thing once you've discovered it, that you shouldn't publish it either. You shouldn't tell anybody because it's a very powerful tool that you have. So for now, we're kind of sitting on that. Maybe when we write the magnetics book, we're going to do that. Okay, where can I find the simulation tool? Go to our website. Send us an email. We can send you a demo. How to clamp. Is there a guide? 50%. To clamp. My interest is transformers. As usually stated, the energy is stored in the gap. I don't know. People spend too much time thinking about what they call their flybacks and their inductors and their coupled inductors and where the energy is stored. Tell you the truth, I don't lay awake thinking about that because I don't care where the energy is stored. We just have a process, okay? You choose the core, you put the turns on, you gap it till you get the inductance. I don't care. I don't care where the energy is stored. So leave that to the physicists, okay? There's a big pile of books over there that you'll see. All right, one of those books, you'll find somebody talking about the energy storage. It's not something you deal with when you're doing design, to be honest. But fun to discuss if you like discussing that. More of a 4-hour webinar. We can do a 4-hour webinar, but we're going to have to charge a fee for that. So that is something we're very interested in doing. We've been talking to somebody else about that recently as well. Shielded winding. If you want a master's in power electronics in the US, Virginia Tech is where I did mine. University of Colorado, I hear, is pretty good. I think Berkeley does it. There's lots of good places. You can put that question also on the Facebook group. Okay, great place for that question. Don't put it on LinkedIn. Don't put it on LinkedIn. Put it on the Facebook group. Every time I answer a question, it goes back to the top of the pile again. Okay, we've still got 270 people in there. There will be a recording, okay, of this talk. You'll get that in about a week. Sam Lowenstein, I can't see what your question is. I can only see your question asking why we don't answer your question. Maybe we got to it. Multi-resonance, got that. How is the core selected? I think we got that. 4-hour webinar, okay, there, got that. What type of snubbers clamps? Well, we went over the RCD, we went over the snubbers. I always try to get away with an RC. Keep it simple, okay? Life is hard in power converter design. Active clamp flyback can achieve 0 voltage switching. Yes, it can. There is a penalty. You saw the penalty. It's got to step down 30 to 1. It's going to have big pulses in the secondary. Those secondary pulses are so narrow that it just doesn't work properly. All right, do I have any experience with single input, multiple output converters? Yes, everything is a multiple output converter that I work with. I have lots and lots of experience. You will find almost nothing written about multiple output converters. And the reason there's nothing written about it is because it doesn't make a good IEEE paper because it doesn't obey the theory. So, I'll bring the questions up here. Sorry about that. It doesn't obey the theory. That's no good. I've got too many pictures of me. What is the big draw for the quasi-resonant to begin with? Well, people go quasi-resonant because they think they want super high efficiency because that's what all the papers talk about. But in the real world, you know, if I'm a flyback in a 10,000 amp breaker, nobody's beating on me for another 1% efficiency. But I'd better not fail. You know, if I'm enabling that much power, who knows what they're powering? Cities, whatever. It's very, very, very expensive to deal with that. So yeah, no quasi-resonant for me in that case. Let me just put the questions over there. You will get the recording in a week. Got that. DZ clamp. I hate the DZ clamp. You know, I just don't like it. I'd rather go RCD than DC clamp because you get another element. There's a lot of EMI energy goes into that Zener. It's got the full voltage of the Zener. It's got a pulse of current that's pretty high, and boom, burst of EMI. Don't do it. You see it in all the app notes because they're lazy. They're semiconductor people. Sorry. I know there's some good semiconductor people out there too, but it's usually just a laziness is the Xena. But it's also dirt cheap. Okay, I don't deal in the dirt cheap supplies. There's nothing I can do to help those designers. Have you seen any negative impacts on emissions? Emissions are emissions. Everything has emissions. Okay, it's a pain, and there's no magic circuit that removes your emissions. Would I use an active clamp instead of an RCD? First, I wouldn't use an RCD unless I had to. Secondly, I wouldn't use an active clamp unless you were paying me lots and lots of money. So, no. And I'm sure somebody come talk about it on our Facebook group about the active clamp. How can we go to 64 duty cycle transformer reset? It's not a transformer, it's an inductor in a flyback. You've got plenty of time to reset. You've got different voltages during on and off. Okay, here's your question, Sam Lowenstein. The controllers I use are getting old and sometimes hard to get. That's not my experience. They're always easy to get. They want to charge you more, but there are so many companies out there using the 3840 series of controllers. There's multiple sources for it, and then there's LTE has a secondary part to it. Yes, they're old, and that's why they're good. They're old, and they're using a bipolar process, and the bipolar process means they're much more noise immune. Okay, they went to MOSFET later on, CMOS process, and supposedly better because it's lower dissipation in the controller. It's much more noise susceptible. What kind of simulation tool do you use? I use RidleyWorks, and then I port RidleyWorks out to LT Spice when you need the extra bit. Okay. Is the converter in DCM mode all the time? No, every converter that's designed in DCM mode, at some point, it will go in CCM. When you start it up, it will be CCM. So if your objective is to never, ever be in CCM, you will fail. Because when it starts up, it's always going to go CCM. All right, so it might go unstable during startup as well. The software is called RidleyWorks. You got the answer there. Dual active bridge. Dual active bridge or phase shifted bridge requires more. Let's read the rest of the question. Yes. Okay, don't ever build a Zeta converter. It's a waste of time. I hate that they keep appearing in app notes. Okay. CPIC, it's a fourth order converter, but sure, if you want bidirectional. I would prefer, instead of a CPIC, I don't know if you want isolated or not, but I'm not a fan of the CPIC, and I'm definitely not a fan of the Zeta converter. I think they're in there for academic completeness from the professors. It's like a chip converter. Okay, almost back down to where we are. What kind of magic happens when we increase the frequency from 100 kilohertz to 200 kilohertz? Everything gets smaller. It's much better at 200 kilohertz than 100 kilohertz. Trust me. And if you haven't done the design, then you just try it. It's just much better. Most of the flybacks are moving up. This old 150 kilohertz limit that people used to have restrict themselves to 150 kilohertz because of the EMI. That is no more. People aren't worrying about that. They switch at a higher frequency. They just filter it more. It's no problem. All right. The dual active bridge or phase shifted bridge. Okay. My first full bridge I built in 1982. If I never build a full bridge again, I'm okay with that. The phase shifted full bridge, they've been around since the 1970s. People seem to be just discovering them, and it's a hot topic these days. They are a pain. They are nice when you've cleaned up the primary. It's nice. It's pretty. There's no snubbers on the primary, but there is pain in the development. Okay, there will be failure during the development. Okay, the dual active bridge is next level pain that you must use a digital controller. I don't think anyone's come out with an analog controller for the dual active bridge yet, and they probably won't. So there's a lot to deal with there. If you're in the 50 kilowatt, 100 kilowatt world, this is what they built. Okay, and they love it. Down in the world where little flybacks happen, you're not going to do that dual active bridge. But it is coming in more and more active, more and more the dual active bridge. We'll probably get it into RidleyWorks eventually. Okay, DT Clamp, we're almost done. Is the full bridge significantly better than the flyback? No. Flyback up to 50 watts or so. Full bridge 300, 400 watts or so. Okay. Is it better? Well, it depends what you like doing. Okay. Blowing up full bridges is not good. It's not fun. All right. I think we've got all the questions here. Sorry I missed these as we went, but it was probably better that way.
Nishant has a question right at the top of the thread again now, Ray.
Yeah, what is it?
He's got three. They're about EMI.
Okay. Layout can change EMI. Yes. EMI increases at high frequencies. No, it changes. EMI is always awful. Okay? So EMI is EMI. When you look at the modern designs, if you come to our workshops, we have all these modern designs sitting on the bench, okay? And we have LLCs in there, and we have interleaved 2-switch forwards. You know, we have all kinds of converters. One thing that is constant on all these designs, the EMI filter is about the same. It doesn't change, okay? So the EMI problem is never going away. You just shift the band of where you're generating the noise. Even if you're switching on 100 kilohertz, the band of noise is much higher than that. It's in the multi megahertz range. Okay, yeah, I see. What do I think about planars? Planars are great. A planar is no longer flat. A planar is just a way of putting the windings in differently. We started doing planars in Ridley Works. So what's my opinion of them? As inductors, they're pretty awful. As transformers, they can work quite nicely, and there's some very nice planars, but John will back me up this. The planars that we see coming in on many of the service supplies that we've got here, they're called planars, but they are cubes. The 3 dimensions are the same. Okay, it's just that the windings are no longer going around the core, they're going that way. They flip them 90 degrees. So you want to call that a planar, it's no longer a flatness issue. It's not a PC board issue. Most people don't use PC boards for their transformers. They're wires and foil for the good ones. PC boards, well, they're just compromised transformers, quite honestly. Voltage mode control for a flyback, why would you do that? Just don't. Okay, current mode control. Every time. I don't know. If you're getting 70% efficiency, are you doing poorly? Well, it's lower than standard. When we do our designs, these are our workshop boards that we do here. When people come in, they wind the flyback transformers in here. And most of the boards are up around 90% efficiency, and that's without using synchronous rectifiers. So, yeah, 70 is a bit low. My first ever converter, 650 watts, it was 76%. So, yeah, 70% is a bit low, but we'd have to figure out why. Lots of companies avoid using snubbers. Well, they're running into a risk. If they're doing dirt cheap designs and they don't put a snubber in under a transient, they may get over voltage. They lose their components. So even if you're doing a DCM flyback, that secondary snubber on the diode, you shouldn't need it when it's DCM, but during startup, it's going to be CCM. You're going to see ringing on that part. Again, there's this obsession, this modern obsession with efficiency that most applications don't care about, to be honest. But, you know, if you don't put snubbers in, you've got EMI. So it's a trade-off. Digital control or controller chips, yeah, you know, when we have our course boards here, you know, you look at that entire circuit, we've got the FETs in red, diode boards there, we've got a control board there. If you want to unplug that control board and put a digital controller, be my guest. You've just changed the chip, in my view. Then somebody's got to write some code on top of it. If your company is good at that, go for it. You know, we got too many things to go. So we're not going to do digital here. Okay, we're not going to do that. It's just too much. If I was to ask to make design again from 31 years ago, it would likely be more dense. Well, not in this case. It was a 10,000 amp circuit breaker, so nobody cared. What would I do to change it? Well, I'd take it to 200 kilohertz. Not much, to be honest. The input bulk cap is the same. The filter elements are the same. You know, you just don't have, you know, when you see papers about the density of power supplies, it's skipping most of the stuff. It doesn't talk about the input filter, you know. 600 kilohertz, that's pushing. Take some experience to get that. So that's good. Do I know about interesting and practical papers on lossless snubbers? Here's a problem in our industry, right? The people that know how to write interesting and practical papers don't write papers and they don't write books because there's no incentive for them to do so. Okay, in the conference track these days, if the paper isn't filled with 10 million equations, it doesn't get in. In the textbook world these days, somebody publishes a textbook and then it's bootlegged almost immediately. So everybody's textbook is online. So it's hard to find good practical papers. We go look up Rudy Severin's work from way back when. Look up Sanjaya Maniktala's books. Very practical. Okay, but university stuff, they're just trying to find a problem to solve and equations, so harder to find. All right. Is there a path that one could follow to know everything about designing a flyback? Yes, there's a path. You get our software. It's quite easy. It takes a little money, but it's cheaper than inventing the wheel yourself again. Everything we know here, everything I've talked about in this webinar is in the software. So I don't know how to say that in more different ways. I think we're good. I think we're good if there's no more coming in. So thank you all for attending. You will get a questionnaire at the end of this webinar asking you what else you would like to see. Send us questions. You can send them to info@Ridley Engineering. And you can come to our Facebook group as well. One more question dropped in here. How to get rid of the ripple in the flyback. You put in the second filter. That's in the software too, and that's in a paper on our website. So thanks everyone for coming. I appreciate you all stuck around for so long with the questions here, and we'll see you next time we do this. And let us know, please, how often you would like to see this kind of thing. We're thinking about once a month or so is about right, because these are a bit intense to do. But thank you all for coming, and we will see you next time. Thank you.